Hello everyone, welcome to this lecture in the Decision Trees from Scratch series. Today we are going to look at the review and recap of what all we have exactly learned in the previous lectures of this series. So I'll be going through the key concepts which we covered and highlight the important things which you need to remember. So if you want a quick review and recap before going for an interview, let's say, this lecture will be perfectly suited for you. As I'm speaking, when you watch this video on YouTube, I'll put the relevant video links for you to refer to. So let's say when we talk about concepts like Gini, impurity, and entropy, I won't be explaining those concepts in this video, but I'll link the thumbnail to the previous videos in this series where those concepts are explained. This video is predominantly to get a brief overview of what all we have learned so that it can serve as a quick summary. So let's get started. The first thing, if someone asks you about, okay, what exactly is a decision tree, you can think of a decision tree as divided into two parts. There is a statement and there is decision which needs to be made. And then this definition recursively applies. So let's say if you have a statement and then decisions are made. Based on those decisions, again further decisions are made. And then the tree continues and continues and continues, and it gets deeper and deeper and deeper as more and more decisions are made. In fact, if you look at many decisions which you yourself might be making in your life, it can be constructed as a decision tree. Do I want to watch this movie? Yes, no. If yes, then what is the genre of this movie? Then further you can go on classifying. In both the categories, you can go on classifying. Okay, so that's the simplest definition of a decision tree. Now, if you look at the types of decision trees itself, there are two major types of decision trees. The first type is called as classification trees. So let me increase the thickness of my pen over here. Yeah, so the first type is called as classification trees, and the second type is called as regression trees. Many students, when they learn about decision trees, they only think that classification is the only purpose of decision trees, but that's a misconception. In fact, decision trees are a very powerful technique for regression tasks as well. So let us see the difference between the classification approach and the regression approach for the decision trees. If you look at the classification approach, basically the main purpose of the classification decision tree is to classify into categories. So, for example, a simplest question here can be, do you want to learn about decision trees? And then it can split into two branches. It can either split into the yes branch or a no branch. If yes, you can continue watching this video. If no, you can pause this video or not watch it. That's the simplest example of a classification tree. And if you understand this example, you can think of so many real life examples, right? Let's say you have a patient or a bunch of patient data, and if you want to classify whether the patient has a heart disease or not, that's a real life classification problem. In fact, there are so many classification tasks all around you, classifying whether it's a cat or a dog, whether brain tumor is present, whether brain tumor is absent, when a self-driving car is making decisions such as, is this a human in front of me or is this another car? All of those can be thought of to be classification problems. And all of those can be solved using classification decision trees. The second type of decision trees, on the other hand, are regression decision trees. In these type of trees, what we do is that we predict numerical values. So let's say, do you want to learn decision trees? Yes, then your age is between 15 to 40. No, then your age is less than 15, let's say. If this is a decision tree, see, we are predicting numerical values here, right? 15 to 40, less than 15, etc. This is an example of a regression tree. Again, if you understand this concept, you can already think about the huge range of applications of regression trees, right? So think about, if you want to quantify the drug effectiveness, and on the x-axis there is dosage level, the age of the person, the gender of the person, etc. So based on many features, if you want to quantify the drug effectiveness level or the medicine effectiveness level, that's like predicting a numerical value. So this is an example of regression, and regression decision trees can be used. Stock market is another example. If you want to have time on the x-axis and the stock price on the y-axis, that is a numerical value, the stock price. So regression decision trees can be used for that task as well. So these are the two types of decision trees, and in this playlist which we created, we looked at both. For the first 6 to 7 lectures of this playlist, we looked in a lot of detail about classification trees, and for the remaining 6 to 7 lectures of the series, we looked in a lot of detail about regression trees. So when we learnt about classification trees, there are some key concepts which we covered. The first thing which we spent a lot of time understanding is that how is the tree split, and so for example, how do we decide the root node, how do we decide the intermediate nodes, and how do we decide the leaf nodes of a decision tree. For that, there are some key metrics which are used by classification trees. One of those metrics is a Gini impurity, and I will link the lecture in the thumbnail above. What is Gini impurity? You can watch the lecture, but it's a measure of the error in classification. The second measure is entropy. Now, both of these measures can be used for classification tasks. And when I show you Python code in a while, I'll show you that when Python makes these classification trees, you can choose which measure you want to use. And I've seen people use both of these, but generally there is a higher preference towards using Gini impurity. There is a lot of similarities between these two. For example, the highest value for both of these occurs at a true probability of zero point 0.5, let's say. You'll understand all of this when you watch these lectures in detail. But the key goal here is to minimize the Gini impurity as much as possible and minimize the entropy as much as possible while building the classification tree itself. And that's the main purpose, or rather, that's the main thing which is optimized when you build the classification tree. In Python, building a classification tree is a very simple command. It's this decision tree classifier, and you have to specify the x data, you have to specify the y data when you fit using this classification tree. But underneath the hood, what Python is also using is that it's using this algorithm which is called R and T, so which means classification and regression trees. So it's using this algorithm, and what this algorithm does is that for classification trees, it tries to minimize Gini impurity or entropy, and for regression trees, it minimizes other and another metric, which we'll come to in a bit. So if you look at this decision tree classifier function in Python, there are different things which you can give. See, criteria. You can specify the criteria to be Gini impurity or entropy, or there is also something called log loss. Usually, Gini impurity is the most preferred one. If you want to learn more about Gini impurity, please watch the lecture which I've linked above, because sometimes questions can be asked in interview about what is the difference between Gini impurity and entropy. The answer to this question is that they are both great measures for finding the error metric, and there are a lot of similarities between them. But Gini impurity is generally more preferred because it has the probability square and it does not have the log value. So sometimes that leads to better results. Although this is not the case for all the problems, and you can generally experiment with both of these methods. So these are two key methods which we looked at the start. But then, as the lectures proceeded in classification trees, we looked at two other very important things. The first is something which is called as cost complexity pruning, or CCP, pruning of the tree. So pruning as a grammatical term means reducing. So cost complexity pruning means reducing the length of the tree, or rather the depth of the tree. And then finally, we also talked about cross validation and testing. So you might be thinking, why is pruning really necessary? For that, when this part of the series ended, we actually looked at a hands-on problem in Python and we coded out an entire classification tree in Python. Again, I'm linking the YouTube video link above in this video, so you can go through that in detail. But basically, what we did in this problem is that we took a real life example of patients and the data from 303 patients with 13 variables such as age, gender, blood pressure, cholesterol level, etc. And the goal was to predict whether these patients would have heart disease or not. And initially, we cleaned the data a bit. We imputed the missing values. So we did some data pre-processing like one hot encoding, and finally we came to building the classification tree itself. Now it turns out that, as I told you, you can just simply use decision tree classifier in Python and just build out the classification tree between the X data, which is the patient variables, and the Y data, which is basically whether heart disease is present or not. But if you don't do any regularization, or if you don't try to reduce overfitting, this is how the tree will look like. Do you see the problem with this tree? It's a huge tree with a huge number of leaves. In fact, if I scroll over to one such leaf, I'm pretty sure that the number of samples in leaves are just one. And usually, having one sample in the leaves of the decision tree is very bad, because you cannot do a division or a split just based on one person's data. This is a classic sign of overfitting. It means that our decision tree is capturing the noise in the data. So that's why you have to take measures to prevent overfitting. And one such measure is pruning, or cost complexity pruning. Basically, what happens in pruning is that you try to reduce the depth of the tree as much as possible while still maintaining a reasonable accuracy. So, of course, you're reducing the training accuracy because you're reducing the depth of the tree. But the whole goal is that even if training accuracy is compromised, you will do better on test data, or you will do better in generalization. So, there is like this struggle between um, maintaining a high accuracy as well as reducing the depth of the tree, or reducing the complexity of the tree as much as possible. This struggle comes up in even neural networks, because we implement regularization in neural networks, right? That leads to a high training error, but also it leads to good testing accuracy. So the general rule is that try to keep decision trees as simple as possible. If a decision tree looks like this, it's overfitting and it will not generalize well. Now, in cost complexity pruning, so alpha is a parameter which controls how much the decision tree is shortened. So higher the alpha, much shorter is the decision tree. Lower the alpha, much higher is the decision tree, or much deeper is the decision tree. So the whole goal of cost complexity pruning is to find the optimal alpha to strike that balance between accuracy and depth of the tree. So you do actually something called cross validation. You do five-fold or ten-fold cross validation to find the best alpha. So here you can see a plot of alpha with the accuracy, and you will choose the alpha with the highest cross validation accuracy. And then you again plot the decision tree with that alpha. So basically, now the only thing which changes is decision tree classifier, and you mention the CCP alpha, which is the cost complexity pruning alpha, which is what you have calculated from the cross validation. So here you see the decision tree classifier function in Python also has CCP alpha. So the main goal is to determine what value to put here, and for that you use cross validation. Now, if you fit the decision tree with this pruning, you will see that this is how it looks like. Much better, right? Compared to the gigantic tree which which was there before. And if you actually plot the testing performance of the shorter tree, it will be much better than the huge tree which we had before. This also leads us to one of the big major advantages of decision trees, which is interpretability. Looking at this decision tree, I can make so many statements. I can see that the CA variable is important, which is if you do fluoroscopy, how many blood vessels light up. The CA variable is important. Then this thal varium is important, which is basically the thallium heart scan. These two, I would say, are the most important variables to determine whether a patient has a heart disease or not. Because these two variables, the CA and the THAL variable, show up. The CP variable, which is chest pain, also shows up at multiple places, indicating that this is also an important variable for determining the whether the patient has heart disease or not. So just by looking at the decision tree, I can say confidently that if given a new patient, you give me three or four values. You give me how many blood vessels light up under fluoroscopy, you give me the results of their thallium heart scan, and you give me the chest pressure value. And then I can kind of confidently say whether the patient will have heart disease or not. When you get neural network predictions, it's very difficult to make interpretable statements like this. And that's one of the biggest advantages of decision trees, and that's why they are also used so much in commercial settings in companies and startups. Because people can ask questions to the decision tree. Why is it working this way? Oh, if some person has a heart disease, which means they are in the left branch here, maybe one of the values here is satisfying, maybe it's not satisfying, that's why they are in the right branch, etc. I've started liking decision trees for this, for their interpretability mostly. But care needs to be taken to avoid overfitting, and pruning is one very important method which you can implement to avoid overfitting. So this, we ended the classification tree segment at these 4 points, where we looked at Gini impurity, entropy, cost, complexity, pruning, and cross validation and testing. After 6 to 7 lectures in the classification trees part, what we did later is we moved to regression trees. I will use a different color here. Okay, so we moved to regression trees, and similar to the concept of Gini impurity and entropy, in the regression trees, the error is quantified by a variable which is called as sum of squared residuals. This is also sometimes called as SR, sum of the squared residuals. So the whole goal in regression trees is to find the thresholds which minimize the sum of squared residuals. That's how decision tree is constructed. That's how a regression decision tree is constructed. And for that also, Python uses, or scikit-learn uses this cart algorithm, classification and regression tree. And the whole goal of this algorithm is that you decide where to make a split based on that threshold which gives you the lowest sum of squared residuals. I'm attaching the lecture link here so that you can watch it, and I'll also put the information in the chat below so that you know which lectures to refer to at which time points. So this sum of the square residuals is an important concept to be aware of and to prepare before the interviews, because it might be asked, and you should know that what's the difference between SSR for regression and Gini impurity or entropy for classification. Now, just like we saw about cost complexity pruning, cross validation testing, even in regression trees, we looked at a real life example and saw the importance of overfitting, regularization, and testing. So let me show you the example which we took for the case of regression trees. So for the regression trees, we constructed a data set like this, which is a quadratic underlying data set with noise added at different stages. And we tried to first fit a regression tree with depth equal to 2, which looks like this. And we tried to map it out to the underlying data set. Then we fit a regression tree with depth equal to 3. It looks like this. Of course, it's a bit deeper. And then we also mapped it out to the underlying data set. And then we asked the question, how should we determine the ideal depth? And similar to classification trees, what happens is that if you, for regression, actually Python has this, or scikit-learn has this method called decision tree regressor. For a classification, it was decision tree classifier. For regressor, it's a bit different, but the arguments are the same if you watch closely. There is also the criteria here, which was there for classification trees. Then there is the minimum leaf samples, maximum depth, etc. So the question is that how can you determine the best depth of the tree? The main thing is that if you don't specify anything, let's say if you just uh, fit a decision tree regressor between x and y data, we have the exact same issue which happened in the classification case. You remember it was overfitting. So here also the decision tree completely overfits the data if you don't do any kind of regularization or pruning. And if you plot the regression tree in this case, again, the same problem as the classification tree. It looks like a huge tree and it's very deep. And if you look at any of the leaves, I'm sure the leaf will have one sample in each. So clearly, this is a case of overfitting, and that we can see now actually because we have added noise to the data set. And if you look at the red predictions, you can see that they are actually capturing the noise. So we don't want that. To reduce the overfitting, we can of course do pruning, which is what I showed you in the classification tree. The pruning of the classification tree, we can do it in regression also. But just to demonstrate something else, what we did was here we looked at a variable called minimum leaf samples. This is basically telling the scikit-learn algorithm that we should not split a tree unless it has more than 10 samples. This makes sure that all the leaves in the tree, which means all the last nodes of the tree, at least have 10 samples. And that prevents overfitting, because now we won't just fit the noise. Now we have the guarantee that if some split is made, it's not just to fit one noisy data set. There are at least 10 samples to justify that split. So minimum sample sleep is one more amazing thing you can do to prevent overfitting. And when you implement this, you will see that the tree depth automatically reduces. Just by adding one small statement here, minimum sample leaves, the tree depth, which was 15 before in this case, it is now reduced by half to 7, and the number of leaves have also reduced. So if you look at the samples in all the leaves, 10, 10, 10, 14, all the samples you will see are greater than or equal to 10 in all the last nodes or the leaves, because that's the criteria which we have put. And now you can actually test it. You can test the, so if you look on the left hand side, the testing error is 0.018. This is the overfit data where we don't specify the minimum leaf samples. But if you look on the right hand side, you will see that the testing error, which is testing mean square error, is 0.013. So the testing mean square error has reduced compared to the testing error on the left hand side. And that reduction is because of this minimum leaf samples equal to 10. So we don't fit the noise, and that's why the decision tree performs very well on test data, which it has not seen. If you look at the training error, on the left side, the training error is 0, but that does not mean anything because it leads to a higher test error. On the right side, the training error is almost similar to the test error. This is usually good. If the training error is similar to the test error, it means that there is no overfitting. But if the data is such that the training error is very very less compared to the testing error, that's usually a sign that there is a huge amount of overfitting, which we should avoid. So in regression trees, similar to classification trees, just using this command in Python, decision tree regressor, is not enough. You can do number of things later to prevent overfitting. So this was an overview of what all we covered in this entire series, which has around 13 lectures so far. And we looked at the hands-on coding example for both classification tree and decision tree and regression tree. I've shared these code files with in the information section for that corresponding lecture. So you will find these code files. I'll maybe share it here once more. Okay, so that brings us to the end of this lecture. I hope you all learned a lot, and especially the short lecture will give a good revision material for you as you're preparing for interviews. There are a number of further things to cover, such as random forest, XGBoost, etc. But maybe we can cover that in separate playlists, because that will require again a bit of planning and bit of structuring like this. So thank you so much everyone, and I hope you learned a lot from this playlist. I'll see you in the next lecture.